March 14, 1943. Somewhere near Frankfurt, Germany, the battered remains of a B-24 Liberator bomber lay sprawled across a muddy field, its massive aluminium frame glistening under the cold spring rain. Lieutenant Elizabeth Mitchell of the 44th Bomb Group, 8th Air Force, had piloted the massive four-engine bomber through the fiercest flak she'd ever encountered over the industrial targets of Schweinfurt, before a lucky shot severed her hydraulic lines and damaged two engines. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Her aircraft, bearing the nose art Liberty's Lady and serial number 4120 3728, a B-24D model, had struck the German countryside hard. Mitchell survived the crash landing and would spend the remainder of the war in Stalag Luft, the prisoner of war camp made famous in later years by The Great Escape. But her aircraft, one of the early production Liberators from Consolidated Aircraft's San Diego facility, was about to embark on a journey that would fundamentally challenge the assumptions held by some of the Luftwaffe's most accomplished engineers and mechanics. The B-24 lay relatively intact in that German field, soon to be surrounded by specialized recovery teams who had perfected the systematic retrieval of downed Allied aircraft across occupied Europe. Within days, this particular machine would be transported to Rechlin, the Luftwaffe's primary testing facility northwest of Berlin, where it would undergo meticulous disassembly using tools and techniques specifically developed for reverse engineering Allied technology. The bomber would emerge as perhaps the most thoroughly documented example of American manufacturing prowess ever examined by German technical experts. Following standard evaluation procedures for captured aircraft, this Liberator was destined for service with one of the Luftwaffe's most specialized technical intelligence units, where it would force German engineers to confront an uncomfortable reality about American industrial automation, manufacturing innovation, and their own increasingly untenable technical situation in the escalating production war that would ultimately determine the conflict's outcome. The story of how captured enemy aircraft became catalysts for technological revelation begins not with Mitchell's forced landing during the spring bombing offensive, but with the Reich's growing realization that the air war was rapidly becoming a contest of industrial capacity rather than merely pilot skill or aircraft design. By early 1943, the Luftwaffe faced a strategic crisis that threatened to overwhelm German air defenses, despite the considerable expertise of individual engineers and the ongoing development of advanced aircraft designs. American bomber formations were penetrating deeper into the Reich with each passing month, carrying increasingly sophisticated equipment whose true manufacturing complexity remained partially mysterious to German commanders tasked with developing countermeasures. Intelligence reports from examination of crashed Allied aircraft provided fragmentary insights into American production techniques, but these examinations often lacked systematic thoroughness and failed to address the fundamental question of how the Americans were producing such complex machines in such staggering quantities while maintaining consistent quality, standards that German manufacturers increasingly struggled to match. Ingrid Keller, an experienced Luftwaffe technical officer, understood that German industry needed more than scattered examinations of battle-damaged components to counter the Allied production advantage effectively. They required comprehensive analysis of intact enemy aircraft, structured opportunities to disassemble these machines under laboratory conditions, and systematic evaluation to discover their manufacturing secrets through direct observation and testing. The concept was not new. Both the Allies and Germans had examined captured aircraft throughout the war, but Keller would organize and systematize the approach in ways that maximized its technical value for German industry. In early 1943, following orders from the Reich Air Ministry, she formed what would become known as Fremde Flugzeuge-Auswertung, Foreign Aircraft Evaluation, officially designated as a specialized technical intelligence unit operating under the Technisches Amt, the technical office of the Luftwaffe High Command. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. This specialized unit received all repairable, captured Allied aircraft that German salvage teams recovered from crash sites across occupied Europe. The unit's mission extended well beyond simple performance testing at secure facilities behind the lines. Keller organized systematic disassembly procedures where captured aircraft would undergo meticulous examination at specialized facilities across Germany, allowing industrial experts to examine these machines down to their smallest components, documenting manufacturing techniques, material composition, and production methodologies that might be adapted for German use. The program addressed a fundamental problem in German industrial production that had become increasingly critical as the war progressed and resource shortages increased. German aircraft manufacturing relied heavily on skilled craftsmen performing complex assembly operations, using techniques that prioritized precision but limited production volume. This approach created superbly engineered aircraft, but in quantities increasingly inadequate to match Allied production. This created a dangerous blind spot when competing against American manufacturers whose aircraft possessed markedly different production characteristics, especially regarding standardized components, automation, and assembly line techniques that enabled massive production scales beyond anything Germany could currently achieve. The recovery operation for Allied aircraft had become highly systematized by 1943, with specialized German salvage units operating across occupied territories under the direction of Bergungsbataillonen or salvage battalions. These teams worked with remarkable efficiency to secure crash sites, assess damage, and transport repairable aircraft to centralized testing and examination facilities before advancing Allied forces could recapture the area. The organizational structure reflected German military thoroughness, even as resources grew scarcer. The scale of Allied air operations over Europe made captures inevitable through sheer statistical probability. With thousands of sorties flown monthly by American and British forces, mechanical failures, battle damage, navigation errors, fuel exhaustion, and weather-related incidents resulted in numerous forced landings on German-controlled territory. Not all of these aircraft were destroyed on impact or rendered irreparable by crash damage. Some pilots, recognizing their situation was hopeless, executed controlled crash landings that left their machines largely intact, sometimes even with minimal structural damage that could be repaired with available resources and components. Mitchell's B-24 fell into this category of repairable captures. The aircraft had sustained damage during the intense bombing mission against German ball-bearing factories, forcing an emergency landing in territory that remained under German control. German recovery teams reached the site within hours, following established procedures for evaluating crash sites. They examined the Liberator carefully, assessed the extent of damage, and determined that despite battle damage and crash impact, the airframe remained sufficiently intact for complete technical evaluation. The aircraft was carefully loaded onto specialized rail cars and sent to Rechlin, where experienced technicians and engineers would begin the meticulous process of documenting and disassembling the massive bomber. Rechlin Testing Center, located near Lake Müritz, served as the Luftwaffe's primary facility for evaluating new German aircraft designs and conducting detailed examinations of captured enemy types. The facility, which had been officially designated the Luftwaffe's Central Testing Center in 1936, included extensive workshops equipped with specialized tools, comprehensive documentation facilities, and technical laboratories specifically configured for evaluation under controlled conditions. Technicians at Rechlin possessed considerable skill in reverse engineering and analyzing Allied aircraft, despite lacking original technical manuals, factory specifications, and manufacturing documentation. The examination process for Mitchell's Liberator revealed technical insights that would fundamentally challenge German assumptions about American industrial capability. The initial exterior examination focused on the B-24's distinctive shape, its high-mounted Davis wing with its unique airfoil, twin-tail assembly, and tricycle landing gear configuration. German engineers photographed every external feature, carefully measuring dimensions, panel alignments, and structural elements before beginning the disassembly process. What first caught the attention of Emma Weiss, the senior engineer assigned to the project, was the remarkable consistency of the sheet metal work across the entire airframe. Unlike German aircraft, which often showed subtle variations in panel fit and finishing due to their handcrafted nature, the B-24 displayed mechanical precision that suggested highly automated manufacturing processes. Particularly noteworthy was the consistent quality of riveting throughout the airframe. Thousands of rivets placed with mechanical precision at exactly identical intervals with uniform compression. This is not handwork, Weiss noted in her initial report. The consistency can only come from automated riveting machines operating with precision that exceeds even our best skilled metalworkers. The speed with which these aircraft are being manufactured suggests extensive use of automation we have not yet implemented at comparable scale. The first phase of disassembly focused on the Liberator's massive wing section. The Davis wing, with its high aspect ratio and relatively thin airfoil, provided the B-24 with excellent high-altitude performance and fuel efficiency critical for long-range operations. German technicians carefully removed the outer wing panels, documenting the internal structure with growing amazement at what they discovered. Unlike German aircraft wings that typically featured complex internal structures requiring skilled handwork to assemble, the B-24's wing utilized standardized internal components, clearly designed for rapid assembly by workers requiring minimal specialized training. The internal structure revealed clever design elements specifically engineered to reduce manufacturing complexity while maintaining structural integrity. Particularly impressive was the wing's internal fuel tank design. Where German aircraft typically used welded and carefully sealed fuel tanks that required skilled metalworkers to fabricate, the B-24 incorporated self-sealing fuel cells that could be manufactured separately from the wing structure and installed as complete units. This modular approach significantly reduced assembly time and allowed parallel manufacturing processes impossible in German production systems. The Americans have designed this aircraft specifically for mass production, Weiss wrote in her technical assessment. Every component shows evidence of having been engineered not merely for function, but for manufacturing efficiency. The modular approach allows multiple teams to work simultaneously on different sections, without requiring the sequential assembly our methods demand. As disassembly progressed to the bomber's 4 Pratt, Whitney Artisans 830 twin-wasp radial engines, German engineers encountered another revelation. These massive 14-cylinder engines, each producing 1,200 horsepower, displayed manufacturing techniques that differed fundamentally from German power plant production methods. The cylinder heads, historically some of the most challenging components to manufacture consistently, showed evidence of automated casting processes that produced identical parts with minimal variation. Karl Hoffmann, the engine specialist assigned to the evaluation team, documented the remarkable interchangeability of engine components, DAGA, characteristic that German engines, with their often hand-fitted parts, could not match at equivalent scale. The twin-wasp engines revealed sophisticated machining techniques that allowed critical internal components to be manufactured to such precise tolerances that they could be assembled without the hand-fitting German engines typically required. These engines were clearly manufactured on automated production lines, Hoffmann's report stated. The consistency of critical measurements across all components suggests precision tooling and quality control systems beyond what our current methods can achieve at comparable production rates. American manufacturers have solved technical problems we are still addressing through skilled handwork. The electrical systems throughout the bomber presented another area where American manufacturing advantages became painfully apparent. German aircraft typically utilized hand-assembled wiring harnesses, with skilled electricians routing and connecting each wire individually during the assembly process. The B-24, by contrast, revealed prefabricated wiring harnesses with standardized connectors that could be rapidly installed by workers with minimal specialized training. This approach dramatically reduced assembly time and significantly improved reliability by eliminating the variations inevitable in hand-assembled electrical systems. The standardized connectors allowed entire systems to be tested before installation and quickly replaced if faults developed, representing a maintenance philosophy that prioritized operational availability through component replacement rather than in-place repair. The bomber's instrument panel and flight controls revealed similar design approaches focused on manufacturing efficiency without compromising functionality. Unlike German aircraft instruments, which often required individual calibration and fitting, the B-24's instruments showed clear evidence of standardized production with interchangeable mounting systems. The control systems utilized clever design elements that simplified manufacturing while maintaining reliability, with standardized components used repeatedly throughout the airframe. The Americans have approached aircraft construction with fundamentally different priorities, noted Werner Schmidt, the systems specialist examining the control mechanisms. Where we optimize each component individually for maximum performance, often at the expense of manufacturing complexity, they have designed entire systems for production efficiency while maintaining acceptable performance. The result is aircraft that may not achieve theoretical performance maxima, but can be manufactured in quantities that overwhelm through sheer numbers. The examination of the Liberators' defensive armament system proved particularly revealing about American production capabilities. The bomber's 10 .50 caliber Browning M2 machine guns were mounted in powered turrets and beam positions that provided overlapping fields of fire against attacking fighters. The turret mechanisms, manufactured by companies like Sperry and Emerson that had previously produced civilian products, demonstrated how effectively American industry had converted to military production. Engineers disassembled the complex turret systems, discovering precision manufacturing that combined electrical, hydraulic, and mechanical components into integrated systems produced on assembly lines. The turrets incorporated sophisticated features like electrical position indicators, hydraulic power assistance, and computing sites that automatically calculated lead for target interception, all manufactured with standardized components designed for rapid assembly. These defensive systems represent manufacturing complexity our industry would struggle to match even in small quantities, observed Anna Fisher, examining the Sperry ball turret from the bomber's belly position. The Americans have somehow solved the production engineering challenges of creating complex electromechanical systems on assembly lines, something our manufacturers have claimed was impossible at industrial scales. As the disassembly progressed deeper into the airframe, German technicians documented the extensive use of aluminum throughout the structure. The material quality remained consistent across all components, revealing America's substantial advantage in access to raw materials. But more significant than the materials themselves was how they were utilized, 26, with standardized extrusions, pressings, and formed components designed specifically to minimize assembly time. The aircraft's construction revealed hundreds of identical structural components used repeatedly throughout the airframe, significantly reducing the number of unique parts requiring separate manufacturing processes. This standardization extended to fasteners, access panels, and internal systems, creating an aircraft that could be assembled rapidly by teams of workers following standardized procedures rather than relying on the judgment and skills of master craftsmen. The entire aircraft reflects a production philosophy fundamentally different from our approach, Weiss summarized in her comprehensive report, where German aircraft represent the pinnacle of handcrafted precision engineering. This bomber embodies industrial automation and standardization that enables mass production without unacceptable quality compromise. The manufacturing technology evident in this single aircraft suggests American production engineering is at least a decade ahead of our current capabilities. The most profound revelations came when German engineers examined manufacturing marks on various components throughout the airframe. These revealed extensive use of transfer line automation, where components moved automatically from one machine to the next in continuous production sequences. Parts showed the distinctive markings of multi-spindle drilling operations, where dozens of holes were drilled simultaneously rather than sequentially, as in German production. Sheet metal components displayed evidence of production using massive stamping presses that could form complex shapes in single operations, eliminating the multiple forming steps and hand finishing that German manufacturing required. Throughout the airframe, engineers found components with part numbers and production dates stamped by automated marking systems, revealing tracking and inventory control systems that supported the massive logistics requirements of high-volume aircraft production. The Americans appear to have applied automobile mass production techniques to aircraft manufacturing with remarkable success, concluded Hoffman after examining components from throughout the airframe. Where we consider aircraft fundamentally different from cars and requiring craft-based manufacturing approaches, they have systematically eliminated production bottlenecks through automation and standardization. The result is manufacturing capacity that outstrips our potential output by factors of 5 to 10, even if we had equivalent raw materials. The B-24's hydraulic systems underwent particularly detailed examination, revealing standardized components used across multiple aircraft types in the American inventory. This commonality of parts between different aircraft models represented another significant manufacturing advantage, allowing massive production runs of identical components rather than the specialized, low-volume parts typical in German aircraft. The hydraulic pumps, actuators, and control valves showed evidence of automated manufacturing techniques that produced consistent, interchangeable components at volumes impossible with German methods. The system utilized standardized fittings and connections that enabled rapid assembly and simplified maintenance, reflecting a design philosophy that considered the entire life cycle of the aircraft from production through operational service. Over the following weeks, the examination team produced a comprehensive 200-page technical report documenting every aspect of the B-24's construction, materials, and evident manufacturing techniques. This detailed analysis made its way to the Reich Air Ministry and ultimately to Albert Speer's office at the Ministry of Armaments and War Production, where its implications were immediately recognized as strategically significant. The report's conclusions were unequivocal. American aircraft manufacturing had achieved levels of automation, standardization, and production efficiency that German industry could not match with current methods. The manufacturing technology gap represented at least a decade of industrial development that could not be overcome in the short term, regardless of German engineering expertise or the skill of individual workers. The report's conclusions sparked immediate concern among senior officials in Berlin. Speer himself requested a personal briefing from Weiss and her team, recognizing that the manufacturing gap represented a strategic vulnerability, perhaps more significant than any tactical or operational challenge. The implications extended far beyond aircraft production to fundamental questions about industrial capacity that would determine the war's ultimate outcome. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. In response to these revelations, Speer organized a specialized technical conference in April 1943, bringing together leading German industrial engineers, aircraft manufacturers, and military production specialists. The captured B-24 components were transported to Berlin, where they were displayed in a secure exhibition hall, allowing German industry leaders to examine first-hand evidence of American manufacturing techniques that had previously seemed implausible or exaggerated in intelligence reports. What we are seeing here represents not merely a different approach to aircraft production, but an entirely different industrial philosophy, Speer told the assembled experts. The Americans have systematically eliminated hand craftsmanship from their manufacturing process, replacing it with automation that achieves both higher production rates and more consistent quality than our methods can match. This is the true strategic challenge we face. The conference examined specific components from the Liberator that best illustrated American production advances. The wing spars, typically among the most labor-intensive components in German aircraft, showed evidence of automated extrusion and forming processes that eliminated dozens of manual operations. The fuselage sections revealed standardized assembly jigs that ensured perfect alignment without requiring skilled fitters to make adjustments during construction. Most concerning to German engineers was the evidence of manufacturing sequences deliberately designed to use semi-skilled labor effectively. American production engineers had systematically analyzed aircraft assembly, breaking complex operations into simple, repeatable tasks that workers could master in days, rather than the years of apprenticeship German methods required. This approach allowed rapid expansion of the workforce as production demands increased without sacrificing quality or consistency. "The Americans are not producing aircraft the way we would if we simply had more resources," explained Weiss to the gathering. "They have fundamentally reimagined the entire manufacturing process, creating systems where the tooling and assembly sequence, not the individual craftsman's skill, ensures quality. This is production engineering at a level we have discussed theoretically, but have not implemented at industrial scale." Kurt Tank, the brilliant designer responsible for the Focke-Wulf aircraft series, examined the B-24's control surfaces with particular interest. His own aircraft were widely regarded as among the finest German designs, yet the manufacturing processes required to produce them limited output to quantities insufficient for Germany's strategic needs. The American approach to standardization and interchangeability represented a path his company had considered but not fully embraced. What we are seeing here is evidence of a fundamentally different relationship between engineering and manufacturing, Tank observed after examining the bomber's ailerons. Where our design bureaus create the ideal aircraft, and then manufacturing attempts to build it, the Americans have clearly allowed production engineering to influence design from the earliest stages. Every component shows evidence of having been designed specifically for efficient manufacturing, even if that occasionally means accepting small performance compromises. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The conference discussions turned increasingly somber as German industrialists recognized the full implications of what the captured bomber revealed. Even if Germany had possessed equivalent raw materials and energy resources, the manufacturing technology gap would have remained a decisive disadvantage. The specialized machine tools, transfer lines, and automated forming equipment evident in the B-24's components represented years of industrial development that could not be rapidly duplicated, particularly under wartime conditions. We must be realistic about what we can and cannot change in our production systems, given current circumstances. Speer concluded after 2 days of technical discussions. We cannot match American production volumes with our existing methods, and we cannot completely transform our industrial base while maintaining current output. We must therefore identify specific manufacturing innovations we can implement quickly without disrupting existing production, while beginning longer-term transformation of our industrial capabilities. Following the Berlin conference, the captured B-24 components continued their journey through specialized German research facilities. The electrical systems went to Siemens laboratories for detailed analysis of American wiring techniques and connector standardization. The hydraulic systems were sent to specialized fluid power research centers to examine manufacturing techniques for precision components. The airframe structural elements underwent metallurgical analysis to determine exact alloy compositions and heat treatment techniques. Throughout this distributed examination process, German engineers consistently reported the same fundamental findings. American industry had systematically eliminated manufacturing bottlenecks through automation, standardization, and production engineering that considered manufacturing efficiency equal in importance to performance specifications. This industrial philosophy permeated every aspect of the bomber's construction, from major structural components to the smallest fasteners and fittings. At the Junkers Aircraft Works in Dessau, manufacturing engineers studying the bomber's construction techniques attempted to implement simplified assembly procedures based on their findings. They created experimental production lines that borrowed concepts evident in the B-24's design, focusing on standardization and interchangeability to reduce the skilled labor requirement per aircraft. These experiments achieved modest productivity improvements, but remained constrained by existing tooling and factory layouts designed around traditional manufacturing methods. We cannot simply copy American methods without fundamentally rethinking our entire production philosophy, reported Heinrich Wagner, Junkers' production director. Their advantages stem not from any single technique, but from an integrated approach where design, tooling, material supply, workforce training, and assembly sequence all align around production efficiency. Implementing isolated techniques without this holistic approach yields minimal improvements. At Messerschmitt's massive Regensburg plant, technical staff applied specific lessons from the B-24 to their Mi-109 fighter production. They standardized certain fasteners and brackets throughout the aircraft, allowing larger production runs of identical parts. They reorganized assembly sequences to enable parallel work on different aircraft sections, reducing overall production time. They simplified certain components to reduce manufacturing complexity without compromising critical performance characteristics. These targeted changes increased monthly output moderately, but still left production far below the rates American factories were achieving with similar workforce numbers. The fundamental constraints of German manufacturing methods remained, tended an approach that prioritized craftsmanship and individual component optimization over standardization and assembly efficiency. The most significant response to the B-24 revelations came from the Reich Ministry of Armaments and War Production, where Speer initiated what became known as the Industrialization Program, Industrialisierungsprogramm. This systematic effort aimed to transform German aircraft production by implementing specific American manufacturing techniques, where possible, while preserving output from existing production lines. The program began with a comprehensive industrial census, documenting current manufacturing methods across all major aircraft producers. Special attention focused on identifying production bottlenecks, operations requiring excessive skilled labor, and components with unnecessary manufacturing complexity. Each factory received detailed analysis of potential improvements, with specific recommendations for implementation. Specialized teams of production engineers visited plants throughout Germany, introducing standardized workflows, simplified assembly sequences, and improved tooling based partly on insights gained from the captured B-24. These changes faced significant resistance from traditional craftsmen and managers accustomed to established methods, but wartime necessity gradually overcame this opposition as resource constraints tightened and production demands increased. "We are not merely changing how we build aircraft," Speer explained in a directive to factory directors. "We are challenging fundamental assumptions about industrial production that have shaped German manufacturing for generations. This transformation would normally require years of peaceful development, but current circumstances demand we accomplish it while maintaining and increasing output under increasingly difficult conditions." By late 1943, the industrialization program had achieved modest but meaningful improvements in German aircraft production efficiency. Monthly output increased approximately 30% across major manufacturers, without corresponding increases in workforce or raw materials. Components standardization reduced the total number of unique parts requiring separate manufacturing processes. Simplified assembly sequences reduced training time for new workers, allowing faster workforce expansion despite the continuing skilled labor shortage. These improvements, while significant, still left German production capability far below American levels. A Messerschmitt plant with 5.0 workers typically produced 250-300 fighters monthly after implementing enhanced methods, while equivalent American facilities regularly achieved 400-500 aircraft with similar workforce numbers. The fundamental industrial technology gap, identified through the B-24 examination, remained a decisive factor that could be narrowed but not eliminated under wartime conditions. Beyond specific manufacturing techniques, the captured bomber revealed something more fundamental about American industrial capacity that particularly concerned German leadership. The aircraft demonstrated a manufacturing system capable of rapidly incorporating design improvements without disrupting production flow, what modern engineers would call continuous improvement methodology. Various B-24 components showed evidence of design, evolution, and manufacturing refinements that had been implemented without stopping production lines or requiring complete retooling. This ability to evolve designs while maintaining production volume represented a flexibility German manufacturing struggled to match with its more rigid, craftsmanship-oriented approach. The Americans have created not merely efficient factories, but adaptive production systems, observed Weiss in her final comprehensive report. Their manufacturing approach allows continuous refinement based on operational experience, production lessons, and material availability, without the production disruptions our methods typically require when implementing changes. This adaptability represents perhaps their greatest advantage in sustained industrial competition. As Allied bombing against German industry intensified throughout 1943, captured B-24 gained additional significance. American manufacturing methodology, with its emphasis on standardization and interchangeability, proved far more resilient to bombing disruption than German production systems. When Allied bombs damaged American-style production lines, their standardized components and documented assembly procedures allowed relatively quick restoration of production at alternative locations. German manufacturing, with its greater dependence on specialized tooling and skilled craftsmen, proved more vulnerable to precision bombing. When key production facilities or uniquely skilled workforce concentrations were lost, the specialized nature of German production methods made recovery significantly more difficult and time-consuming. The craftsmanship that created exceptional individual aircraft became a strategic vulnerability when subjected to systematic attack. In response to this growing vulnerability, German authorities accelerated factory dispersal efforts, relocating production to smaller, distributed facilities less vulnerable to bombing. This dispersal, while necessary for survival, further disadvantaged German production methods that relied on centralized expertise and specialized equipment. Distributed facilities struggled to maintain quality and efficiency without the concentrated technical resources of major production centers. The most lasting impact of the B-24 examination came through its influence on younger German engineers who would later shape post-war industrial recovery. Many who participated in the evaluation program or implemented changes based on its findings recognized fundamental truths about modern industrial production that transcended immediate wartime circumstances. Anna Schmidt, a junior engineer who had worked on the B-24's electrical system analysis, would later help establish manufacturing standards for the German automotive industry during the 1950's economic miracle. What we learned from American aircraft, production in 1943 formed the foundation of modern German manufacturing philosophy, she recalled in a 1978 interview. We recognized that quality could be designed into production systems rather than depending solely on individual craftsmanship, a revelation that transformed our approach to industrial engineering. By early 1944, the captured B-24 components had completed their journey through German research facilities and been thoroughly documented in technical reports that influenced production throughout the remainder of the war. The physical components were ultimately destroyed during Allied bombing raids that systematically targeted German research installations during the war's final year. The bomber's legacy, however, extended far beyond its physical remains. The technical insights gained from its examination influenced German industrial policy during the critical period when production priorities shifted from quality to quantity under increasing Allied pressure. While unable to close the fundamental industrial technology gap, the lessons implemented from the B-24 examination helped German factories maintain output levels that would have been impossible with unmodified traditional methods. For the engineers and technicians who participated in the examination program, the experience fundamentally challenged assumptions about American industrial capabilities that had been reinforced by years of propaganda. Official information had consistently portrayed American manufacturing as capable of producing high quantities of adequate equipment, but fundamentally incapable of sophisticated engineering or precision manufacturing. The B-24 systematically demolished these comfortable assumptions, revealing an industrial system that had successfully merged mass production techniques with complex aerospace engineering requirements. The bomber demonstrated how American factories had solved technical challenges German engineers considered impossible to address through automated methods achieving both quantity and consistent quality that contradicted every propaganda statement about American industrial limitations. What impressed me most was not any single technical feature, but the integrated manufacturing philosophy evident throughout the aircraft, recalled Hoffman in post-war interviews. Every component, from the smallest electrical connector to the main wing spars, reflected a unified approach to production engineering that considered manufacturing efficiency and performance requirements as equally important design factors. This represented industrial maturity we had discussed theoretically, but had not fully implemented. The strategic implications of the manufacturing gap, revealed by the B-24 examination, extended far beyond aircraft production to fundamental questions about industrial capacity that ultimately determined the war's outcome. American factories were producing not only B-24 Liberators, but B-17 Flying Fortresses, P-51 Mustangs, P-47 Thunderbolts, and dozens of other aircraft types simultaneously, each in quantities that individually approached or exceeded total German aircraft production. This overwhelming industrial advantage, clearly evident to those who examined the B-24 in detail, created strategic reality that no tactical innovation or individual heroism could overcome. German pilots might achieve remarkable kill ratios and demonstrate exceptional skill, but they faced opponents whose industrial base could replace losses at rates German manufacturing could never match, regardless of technical adjustments or production refinements. Lieutenant Elizabeth Mitchell's B-24 Liberator, serial number 41-23-3728, had an extraordinary afterlife following her forced landing in that German field. From a crashed bomber lying in the mud, it became an instrument of revelation for German industry, concretely demonstrating American manufacturing capabilities that no amount of propaganda could dismiss as exaggeration or deception. The aircraft served this important educational role until its component parts were scattered across German research facilities and ultimately destroyed, having travelled extensively throughout German industrial centres and provided sobering, concrete evidence of American production advantages to hundreds of German engineers, managers, and political leaders responsible for wartime production decisions. The story of the captured B-24 and its examination illustrates how even sophisticated industrial nations can develop blind spots regarding competitor capabilities when ideological assumptions remain unchallenged by direct evidence. German industrial leaders, operating within a system that emphasized craftsmanship and engineering precision, struggled to recognize or accept fundamental changes in manufacturing philosophy until confronted with physical evidence that could not be dismissed or explained away. The B-24's journey through German technical facilities represented a systematic attempt to understand and counter Allied industrial advantages through production innovation. The program demonstrated professional thoroughness and technical competence in analyzing captured equipment, identifying significant manufacturing differences, and implementing targeted improvements based on these findings. Yet this technical proficiency and systematic approach ultimately could not overcome fundamental industrial disadvantages rooted in decades of different development paths. The manufacturing technology gap identified through the B-24 examination represented industrial evolution that could not be duplicated quickly, particularly under wartime constraints and increasing resource limitations. For modern observers, the story offers valuable insights into how industrial competition drives innovation and how different manufacturing philosophies reflect broader cultural and economic frameworks. The American approach, emphasizing standardization, interchangeability, and production efficiency, emerged from a society with labor constraints and abundant resources. The German approach, prioritizing craftsmanship and engineering refinement, reflected a tradition where skilled labor was relatively plentiful but resources more constrained. Each approach offered specific advantages, but wartime conditions dramatically favored the American system's ability to expand production rapidly while maintaining consistent quality through standardized processes rather than individual expertise. This fundamental difference, clearly revealed through the B-24 examination, represented perhaps the most significant single factor in the ultimate Allied victory. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.